So remember, this is General Chemistry 2. There aren't any exam retakes, right? And there aren't any substitutes or anything oddball things going on. So every exam counts. So you want to make sure we do the best we can on them. So the Thursday at 6:30, we're going to be doing some similar stuff. We're not going to have time to get through every type of question today, but we'll have a lot more and different questions there on Thursday. But let's take a look at this. Now, we can work on them together, or we can work on it as a class, or you can work on it with the folks around you. Is there a preference? Does anybody care? Class? Seems like class you get more done, right? Otherwise, Eric just sits there and blabs. Okay, so let's start with the first one. For the below equation, give the expression for the equilibrium constant Kc. So go ahead and write it out. Write what the Kc expression you think it should be. Kc is, Albert, what did you say it is? Products over reactants, but more specifically, what did you write there? Good. Notice, he noticed this. He says, no, not that guy, so keep going. The H2O and the CO2. And that's it, right? Is that what you wrote? You wrote Summer? Okay. So you can have it over 1 or just erase all that stuff, right? Okay. Victoria. Well, go ahead and answer the which of the following, which if any reaction would almost go completely to product at equilibrium? Which, if any reactant, Victoria, would go almost completely to product at equilibrium? They also call this going to completion. That's also how they reword this. Okay, now what was the trick to doing this? What did it mean? You want mostly what when the equilibrium is reached? You want pretty much all product. So Kc's got to be really big. And which one would that be? A, yeah, 10 to the 113th. So you should pick A. They also say go to completion. That's another way for them to state that exact same thing. But yeah, because it's really because of what Albert said. Albert said K's are always what over what? Products over reactants. So you're going to have a really big number all over a really small number. All right, and you divide the two, you get a really big number. So K's are going to be huge if you want all product. Okay with that? AJ, makes sense? All right, 32. What is the conjugate base of pH 4+? So you're regarding it as an acid, I guess, if you want to write the conjugate base. Write down your answer. Okay, Lauren, what'd you write? Just asking Albert. Now, the more talking you do in here, the better. The psychologists say it's just as valid, just as helpful to you to explain this to somebody else as it is to listen to the answer. Sounds odd, but they say that. So the more talking you're doing in here, the better off you are. If you're not sure, see if the folks around you have the same answer. All right? Is that what Maria says? Is that what Jasmine says? Lauren says pH 3. Albert's convinced her. Do you agree? pH 3 is right. Because if it's an acid, right, you have to take away not just an H, you got to take away an H plus. So you have to subtract 1 from the charge because you're removing an H plus. Get an H plus out of there. Pull an H out, but also subtract 1 from the charge. Remove a plus 1. All that's left is pH 3. Write products for the below reaction and indicate the direction of the reaction. So we've got F minus plus HSO4 minus. You're supposed to predict the products and also the direction of the reaction. Okay, now Brandy, I don't know if you remember doing this, but if this was a test question, you have something to complain about. What do you have to complain about? Dang it! Give me the freaking fill in the blank. Chart, the table. The table of what? All those conjugates, all the acids and all the bases, and they're listed in order of strength. Strength, strongest to weakest. Because you always draw your arrow pointing towards what? The weakest acid. That was that's how we did it. So figure out what the products are, identify what they are, whether they're acting like an acid or a base, and then draw your arrow towards the weakest one. Now, I'll show you the table. First, just write down what you think the products are. Then I'll show you the table, because I've got it ready for you right down here somewhere. So write down what you think the products are, and then I'll show you the chart. And see if the folks, go ahead and ask the folks around you. Here's the chart. Oh, they're marked too. I don't know if that's going to help you. That's okay, they're marked. All right? It's kind of a hint there. Those are the acids that we're comparing. If you're comparing those marked acids, you're doing it right. If you're comparing those marked acids, you're doing it right. Are you comparing those two marked acids, Monica? Did you end up comparing these two acids, HF and HSO4? You did. Okay. So you ended up pointing the arrow towards which one? HF. All right. The weakest is at the bottom. So HF is closer, so you should be pointing your arrow towards HF. Okay. Now, how do we end up with those in the first place? So one of these compounds didn't have a choice. Which one was it? The F. The F has no choice. Because the HSO4, the hydrogen sulfate, he can go either way. He could give up that H, or he could accept an H, but not the F. F has to act like a base. So you put base on it. That means this guy has to be a what, Maria? Has to be a acid. So if that's a base, that means you're going to have to make HF. He's got to be his conjugate acid. Right? Those are our conjugates. And then this guy has to be a conjugate base. So if he's going to act like an acid, you're going to make SO4 with a -2. And Monica said the arrow points to the HF. That was the weaker one, right? This one is weaker. He's the weaker acid. That's why we point him towards him. Make sense? Did I lose you, AJ? Does it make sense? Okay. Circle the stronger acid. Circle the stronger acid. And then, oh yeah, that'll be available to you. Eric, which one did you circle? He says the TE one. Why? What's that? Larger central atom, right? Now, to get to that point, though, you have to. Now, there's some questions you should be asking yourself before you jump to the bigger atom answer, right? And he's right. TE is bigger than S, so he's right. But start out how I start out: number of hydrogens equal number of oxygens, but there aren't any, and then it comes down to that one, right? That's how my brain works. I don't know why I start that way, but that's how it works. So I get to do the easy ones first. That's why I do it that way, because those are the easy ones. But then that TE is so much bigger. So why does that make this more acidic? Because it's a weaker what then? Bond. That H is flopped on there. The bond is spread out, dispersed over more space. It's weaker. So it falls off easier, so it's more acidic. Good. We're definitely not going in the order of how it was presented in class. And notice, too, look how some of these questions are. Are there going to be 10 questions on the test? If there was, you could be out of here in 5 minutes, right? So there's going to be more than 10 questions, because look at some of these, right? It's conceptual. What are the concentrations of hydronium and hydroxide in 0.045 molar per chloric acid? Okay, now to do this stuff, again, you'd have a complaint here. What did you complain about here? The equations. Exactly. Okay, so let's give them to you here. We've got several. Oh, I'm running out of space here. I start over here. One of your answers here, you're on the right track, Ramiro, if you did not use your calculator to get one of your answers. Which one? The hydronium, right? Because HClO4 is a strong acid. And that's all. We haven't talked about problems with any other type of acid, so I have to be giving you strong acids, whether you have them memorized or not, right? That's all the only acid we can give you right now. Exam 3 will be a different story, but not right now. So he's right. Just because it's a strong acid, you know one of your answers already. Oh, they wanted hydronium, but it's the same thing, right? I wouldn't take any points off if you did that, but I guess you should write H3O+. But you got to get the hydroxide. several ways you could get it. Some are easier than others. Summer, did you get an answer for hydroxide? What did you get? Hydroxide is 2.2 times 10 to the negative 13, big M. Is that what you guys got? Everybody else? All right. Probably just, which equation did you use to get it?
I used the 1 times 10 to the negative.
Okay, she used this one. Yeah. So she divided 1 times 10 to the negative 14 by 0.045, and she got it. Mari, did you get it? Okay.
If you have a strong acid with 2 H's, you have to double the concentration.
Okay. Good question. If you had 0.1 molar H2SO4, what did we, so he loses 1 H, he becomes HSO4 minus, right? Is HSO4 minus on your list of strong acids? No, only H2SO4 is. So when you have 0.1 molar H2SO4, H plus is 0.1 molar. But I'm not going to give you that because it's really a little bit higher because you're getting some from this one too. So that's a complicated question. It's going to be roughly very close to 0.1, a little bit higher though, because you have also this acid. But it's we're going to have to, we'll know how to answer that for the next exam. But we're not there. I won't be giving you that one. Okay. I'd say this question is about as complicated as these pH equations can get. What is the hydrogen and hydroxide ion concentration if the pH is 11.63? He was not sure. Man, let me help you out. Mm-hmm. And that'll be equal to your hydrogen ion concentration. Yep. Yeah. See if we have some answers here. We need a hydrogen ion concentration and a hydroxide. Okay, Cassandra, did you get one of these? Either the hydrogen ion or the hydroxide concentration?
Yes.
Which one did you get? Okay. 2.37.
And then I got 4.7.
Oh, so hydrogen is 2.37, and then hydroxide is
4.27.
Oh, I see what she did. Okay, if you this number, where do you get this number from? You took,
I used the equation.
you subtracted this from 14. Is that what you did?
I used the equation like 14 equals pH.
Okay.
Oh yeah, she didn't finish it.
Yeah, he didn't finish it. Because what you got was you put 11.63 in for him, and then you got POH.
Yeah.
So POH is 2.37.
Oh yeah, sorry. Yeah, that's what I meant.
Okay. So that's and that will give us
The OH.
the OH. Exactly. Okay. What did we say it was? 2.37. That will give you the OH. That's one way to get the OH. So how do you get the OH out of this? Yeah. 10 to the negative POH is equal to concentration of OH. So 10 to the negative 2.37. Is that the 4.27 number? Does that work? Okay. Oh, and I'll get a point off because I didn't put a big M. Okay. Then hydrogen ion, what did you get, Jasmine, for the hydrogen ion? Oh, what did you get? We'll find out. She doesn't sound confident though. But it's right. Okay. Now why is it such a dinky number? Because that's right? Isn't that what makes you feel? Ugh. Why is it dinky? Why is that right? Because the pH is really, really basic. The pH is really, really high. This is a really basic solution. 11.6. So it should be a very small number.
Was this to the negative 14 or 12?
I got negative 12.
I don't know.
Yeah, negative 12.
I see a lot of negative 12. We better calculate it. Because several people are getting 12, some people are getting negative. So it'll be 10 to the negative pH is the hydrogen ion. So 10 to the negative 11.63. Make it negative. Shift 10 to the x. 2.34 times 10 to the... Yeah, did you catch it now? It is 10 to the negative 12. That's right. That is right. Okay. All right. What are the general temperature and pressure conditions for an optimum production of nitrogen gas in the below reaction? Now, what kind of possible answers are they looking for? Low temp, high temp, low pressure, high pressure. That's what they're talking about. So ask the folks around you. Someone's got to remember how to do this. Okay. Let's pick on Mari. Let's do the temperature one. If you remember doing these, the temperature one is easier than the pressure one, I think. She says low. Did I circle low? Everybody agree? Eric's saying no. Eric's saying high. Okay. What's the way to make these work is to figure out, do I have too much reactant? Do I have too much product? Do I have not enough reactant? And that's what makes things shift, right? If I have too much reactant, it shifts to the product. If I have too much product, it shifts to the. If I have not enough, remember it's at equilibrium right now. So I can actually have not enough product because I suck something out. So if I have not enough product, it's going to shift towards the. If I don't have enough product, it's got to shift to product to replace it, right? If I have not enough reactant, it's got to shift to the reactants because I don't have enough. So you can actually remove stuff too. Okay, it kind of goes both ways. So the temperature has, you look at what to answer this? Look at the delta H. Okay, because this tells you whether heat is a reactant or a product. Then we know how to play the game. Is heat a reactant or a product with that delta H? It's a reactant. So you actually write the word heat over here. I strongly suggest it because I think it's easier. I write the word heat over there. So heat is a reactant. And you just pick one. It's always easier to add stuff than it is to subtract it. Just mentally, it is for me. So you dump in a whole lot of heat. Temperature's really, really high. What's the effect? Is it what you want? If you dump in a whole lot of heat, then you have too much reactant, shifts to the product. Is that what we want? No. Because, well, let's see. Optimum production of this thing. So you find him. There he is. He's a product, so that's what you want. You want optimum. You want a lot of products. So crank up that temperature, right? Get too much reactant. Get the equilibrium will respond to remove that stress. Pressure. Did the delta H have anything to do with the pressure answer? No. What did have something to do with the pressure answer? The gases, yeah, molecules, gases, the number of molecules of gas on each side. Okay. So on the reactant side, I've got how many gas molecules? Eric says 4. Do you agree? Yeah, pretty much just add the stoichiometric coefficients, right? Or somebody, AJ said it? Somebody said it. 4. All right? Just add up this, what do they call these? The stoichiometric coefficients, right? The product side, you have how many gas molecules? All right, 3. Duh. Molecules. Okay. Now, this is where it gets confusing, I think. I think it's easier just to pick an answer and see if the effect gives you what you want. So in other words, let's just pick an answer. It's always easier to pick high for some reason, I think. See if you pick high. So you're going to really change the pressure on this thing, make the pressure really, really high. Well, this pressure's pressure. You can't tell what gas molecules are creating the pressure. But if the pressure is way too high, the system's going to respond to reduce that pressure. If you make the pressure way too low, the system has to respond to increase the pressure. Make sense? So if I'm going to make the pressure way too high, that's the stress. Too high pressure. I have to reduce it. If I make the pressure too low, that's the stress. Too low of a pressure, the system's going to respond to increase the pressure. It's weird how the system can actually respond to increased pressure. It can. The only way it can, generate more gas molecules. That would increase the pressure, right? Okay, so let's pick one. I think it's easiest to crank up the pressure. System has to respond to reduce it. Well, it would shift to where then? To products. It would shift to where there's less gas molecules, because there'd be less pressure over there. So if you crank up the pressure, system has to respond to reduce it. And that's what we want. So we guessed right. Right?
So it would have, like, for example, 6 gas molecules on the product side and the 4 gas.
If you had 6 over here and 4 over there, then if you crank up the pressure, it's going to respond to reduce the pressure where there's less gas molecules. Then it would go over here, and that's not what you want. Then you'd circle the answer low pressure. Right. Okay, but there's 3 there, so we're okay. Okay. So here's a wordy word question here, right? The reaction of SO2 with oxygen, they tell us, they give us the reaction in red, and then I give you the moles of all this stuff. What is the composition of the equilibrium mixture? And I give you the answers. Now remember, I'm the devil's advocate. I want to make this as complicated as possible. Oh, it's a big test question. And you're expecting, oh, Smith is going to give me a really hard test. And there's going to be that, what's the Q word? The type of equation has x squared and all this stuff in it. Quadratic. And then you got to use the negative b plus or minus square root of b squared minus 4ac over 2a, right? You got some ugly stuff coming at you. Yeah, that's why you got to read these questions careful. So read this out and see what type of question this is. All right? Okay. Now, well, we can make a mole table, or we can make a concentration table. Either one will be okay. But if they don't tell us volume, we don't have any choice. We have to make a mole table. But is this an ice problem? Yes. Why is it an ice problem? Equilibrium composition. Exactly. So I don't... Whenever it says equilibrium, whenever it says what's the composition at equilibrium, it wants you to find out, give you all these answers. What's the concentration, or how much do you have of every single reactant and of every single product at equilibrium? That's an ice problem, right? So, hey, if it turns into a quadratic problem, it turns into one. You don't have any choice. You approach all these the exact same way, right? Approach them all the exact same way. And if it turns into a big, ugly question, it does. You don't have any control over that. There's nothing to memorize. So set up your ice table. Set up your ice table. See how ugly this thing's going to get. Or not ugly. You'll find out. So Vanessa, did you get your ice table set up? Not yet. Maria? Yeah. Read the question careful to figure out what's in the initial row. Also, when you're filling out the ice table, Do we put moles or do we put big M in there? It'd be nice to put big M. So when they tell you a volume, you do it. But they didn't tell us a volume here, right? So we just have to put the moles in. We don't have any choice. Make sense? So we're just going to put moles in. Now, what would you put in the initial? Vanessa, what did you put in the initial? 0.0524 under the SO2. Okay, then keep going. Under the oxygen. On the line under the last one. There must not be any there. Okay. So there, you agree with Vanessa's numbers? Victoria, you agree with Vanessa's initial amounts there? Okay. Good. The change row, what did you put in there, Lauren, for the change row? Negative 2x. Negative x plus 2x. Okay. So, and we have a number of different variations of this. Sometimes it turns into this big, ugly quadratic formula. Sometimes it doesn't. But nothing changes. If they give you a volume, you put in big M numbers in there instead of moles. But they didn't, so we just have to put in moles. You always put in the initial amounts, and the change is just how she did it. Minus for reactants, positive for products. Use the stoichiometric coefficients to determine whether it's 2x or what. And then how do you always get the E row? Every single time. How do you get it? Add them together, right? So if you approach this the exact same way every time, and you read the question carefully, look at this part. You did not use this number in the ICE table because it didn't ask for it. That's not how you approach these. You fill out the I row by putting initial amounts, change row by putting negative x, positive x for products, and then you add the two up to get the E row. Right? Okay, so we'll have 0.0524 minus 2x, 0.0262 minus x, and 2x. There it goes. And then you have to find your x. There's going to be two ways to find your x. Either they're going to tell you what one of these are. In this case, they did, what Summer said. She noticed that that is 0.0311.
But that's 2x.
That has to equal 2x, yes. Right? And if they wouldn't have told us this, they would have given us what? KC. Summer's right on. Right? If they wouldn't have told us one of these, they're going to give you KC. Then you have to substitute all these into the KC expression. And that's when it gets ugly. Right? And I'm sure we'll have some of those. So solve for your x. And once you get it, just substitute into each one of these, and you'll have all your answers. And hopefully it'll match what's up here. All right, make sure when you get your x, you got to divide by 2. Right? It's not, x is not 0.0311. Should work. And if you got it, if you got the answers in green, see if you can set up this one. All right? And if you set it up, you should be able to get to this point. See if you can get to that point. We're not going to have time to finish this one, but it'll be a good practice. Right? Set up your ICE table. Plug in the initial row, change row, and notice they gave us moles and volume so we can find concentration, which is important because we have to plug it into the Kc expression. Yeah, but this answer, he will be 0.0311.
Yeah,
right?
that's what I was wondering.
Yep, he will be 0.0311 because he's 2x. His answer is 2x, which is 0.0311.
Do you set up the ice table with the moles for the first?
I would set up the ice table with a big M right away.
Oh.
So I would find those initial concentrations in moles over liters. Otherwise, you have to write the ice table twice. That's too much work. All right. So we're about out of time, but you have everything you need to see if you can get the right answers here.